Energy it's a tough concept for students. I mean, it's a tough concept for me because you can't hold it in your hand. You can't see it, but it still exists. If we were in a physics class, and I would not be in a physics class at this point in my life, I would give you this definition of energy: the capacity to do work. Physics was not my shining moment. For our class, a better definition is that energy is what moving electrons hold, transfer, and share in the universe of matter. Therefore, work is the process of expending the energy held by your ever moving electrons. The most important thing for us to remember is that energy is like a currency for bonding and making and breaking molecules. As we're going to learn, energy can be trapped in bonds or it can be released from those bonds. What I have here in these pictures are two examples of energy that we as humans can detect. The lunchbox, which looks very tasty right now, it is full of chemical energy. And since it does look vegetarian, all that chemical energy was made by photosynthesis as plants trapped solar energy into ATP. The other picture is energy less useful to us, but that energy that's produced by lightning. Both of these items contain energy and are able to be perceived by humans. As lightning strikes, you see the energy being given off as light. And as the thunder claps, you hear the sound energy being given off as the rolls of thunder. So, again, if we were in a physics class, we would concentrate on types of energy, potential and kinetic. But here in A&P, we'll more constantly encounter the typical forms of energy. All right, so let's start with the types of energy. The terms potential and kinetic refer to energy that is being stored and energy that is actively being used. You could also say that potential is the energy held by a stationary object, and that kinetic energy is energy held by an object in motion. But remember, there are things in this world that humans can't readily detect that are in motion, like the movement of electrons. So even though a human body might be dead, the electrons of those atoms contained in that body still remain in motion. That body has energy. And all of the things that decompose it are going to use that energy. Sparkzilla here is not alive, sadly, but Sparkzilla is a great example of potential and kinetic energy. You wind Sparkzilla, turning the crank, and the kinetic energy of the motion of your hand is stored into the wind-up mechanism within Sparkzilla. Now, Sparkzilla now contains potential energy because it's ready to lumber forth and emit sparks as soon as you switch the lever. As Sparkzilla does lumber forth and emit sparks, it shows us the kinetic energy of motion and sparks that was converted from the potential energy stored in the wind-up mechanism. If you play with Sparkzilla too much, the metal of his body starts to warm up. As the potential energy turns into kinetic, some of the energy is lost as heat. And this is true for everything in the universe. When we change energy from one form to another, heat is lost. This is why you are 98.0 degrees. Now comes the more complicated part. Let's draw together a terrible picture of your brain and the little brain. Let's draw the spinal cord. I'm going to draw a terrible foot here, and I'm specifically going to indicate a muscle that is in your toe. Oh, wait, I forgot the nerve that starts in your brain, travels down your spinal cord, travels out your spinal cord, down your leg, and all the way to the muscles. So this is a nerve. And this little indication here is a muscle that will contract. All right, now comes the more complicated part. When you eat, you trap the chemical energy of your food into the ATP of your cells, right? So that's chemical energy. You use that energy to send an electrical current from your brain down the nerve to the muscle in your big toe. That's electrical energy. Your big toe muscle then contracts, and that's displaying mechanical energy. As the contraction happens and ATP is used, some heat is let off, because as you change forms of energy, some heat is always let off. And that is radiant energy. Endergonic reactions are reactions that trap energy. These are also called anabolic reactions because they build molecules. And many of you may have assumed that from knowing that anabolic steroids help build muscle. Anabolic reactions are also called synthesis reactions, which is a word that just simply indicates the building or manufacturing of something. Students usually pause at the word reduction and they think that I've made a mistake, which is completely possible. I'm not infallible. So this word reduction does not mean to make smaller in this context. In this context, reduction means to gain electrons. And in the action of gaining electrons, a molecule would become more negative or be reduced. So most reduction reactions are anabolic, most. These types of reactions are, all three of them, are abundant when you're a growing child. As a child eats proteins, they're broken down into amino acid subunits. And then those amino acids, here are those amino acids, those are then used by the child to build up the proteins that the child may need in their body at that certain time. Exergonic reactions release the energy that endergonic reactions trap into bonds. These are breakdown reactions, also known as decomposition, a word that I'm going to assume you're probably aware of, and catabolism. As I burn wood in my wood stove, the energy trapped in the bonds that the tree formed from photosynthesis, those bonds are broken down, releasing that energy as heat and light. And these are the types of reactions that your digestive system does, mostly, to break down your food and harvest that chemical energy trapped into the bonds. Opposite to reduction reactions. These are reactions that are called oxidative, where molecules are donating or giving away or being robbed of their electrons and becoming more positively charged. The picture that I have here, many students look at it and they're like, that looks like the picture of the previous slide. Actually, it's the opposite, because these are breakdown reactions. This is a picture of a large protein molecule being broken down into its amino acid subunits.